move back for this one. I'm gonna center myself. Hold on, let me. We can leave it like that. Okay. Let's recline the chair. Actually, let's get some sip of water in this just before we start. And let's close the door. Okay. So, one more sip. Needed that. Alright. So, got a new haircut. Let's get the lighting just right. So, new haircut. Feel real good. Feeling great. In today's video, I just wanted to cover a couple things I learned today and try and really justify what I learned so that I feel comfortable explaining it, and I know that I've solidified my learning. I forgot I had the chair in recline mode. You know, let's stand up for a little bit. Stand up for a little bit. Keep it a little bit more serious. So, I'll start off with some calculus stuff that I learned today. Basically, we're going through limits and discussing continuity at certain points in graphs, and as you approach certain asymptotes, how you can justify the function at those points. And so today I was evaluating limits, and I had to work with direct substitution, factoring, one-sided limits, indeterminate forms, and infinite limits. So as x approaches infinity, and then you kind of just do a little arrow going up towards 0, and I'll explain why. So let's say you were given the function 2x cubed, so limit as x approaches infinity, 2x cubed plus 3x squared plus 7x over x squared, over 3x cubed plus plus x squared. And let's say it was asking you to evaluate this limit as x approaches infinity. So a neat little trick that you can do is essentially just set the every variable and divide it by, let's rephrase that. So first of all, find the largest degree term in the denominator. So in this case, in our example, it's 3x cubed. And you're going to divide, disregarding the coefficient of 3x cubed, you're going to divide every variable, let's say, or every item in the numerator and the denominator by x cubed. And what you can notice is that as x approaches infinity and you're dividing each one of these, because the numerator is a degree larger, other than 2x cubed and 3x cubed, which the x cubes will cancel out and you'll just be left with 2 over 3. But what I really want to get across here is that you will have x approaching 0. So let's just take the second variable in the denominator, so x squared over x cubed. Because x cubed is a degree larger, it'll exponentially increase much faster. So as you go further, like let's say you put in 100 million as x, for example, x cubed is going to increase so much faster, so that entire variable is going to approach 0 that much faster because the denominator is going to be much larger. So that was really one of the first things I learned today, and then I had a question that I asked one of my friends about a limit that was 3x over x minus 2. So you obviously have a vertical asymptote at x equals 2, and because it's asking you as x approaches 2, the limit is as x approaches 2 because you can't set that or else it'll be undefined. and because my course is calculus, right? Calculus and vectors. We're working with how to deal with those vertical asymptotes. And so what he kind of walked me through was you can't use direct substitution, because if you substitute 2 in for x, you're just going to get 0 in the denominator, and that helps nobody. It's undefined. You can't factor anything because everything is simplified. It's at its most simplest form. And you could try and rationalize it, but even if you did, you'd be left with the same exact thing. And so after you've kind of walked through each and every process of how you'd approach these, you can't use a let you method in this case either, because there really is nothing for you to let you equal. Even if you try and do that, it won't work. So what we concluded was the limit just does not exist, and I found that a little bit hard to like wrap my mind around at the beginning, just because when I was approaching the problem, I was approaching like any other problem, and I went through the same type of steps, but I couldn't just fathom that the limit just didn't exist. So after he explained it to me, I understood why it didn't exist, and I just wanted to share just how I kind of walked myself through that process. And then today, I went to the gym, of course. I closed at 6, and I was there at 5:30. It was like a 15-20 minute workout, but I supersetted everything. Like, I'm talking every exercise, just back to back to back to back. No rest. Still got my water, and the music was nice, and I enjoyed the workout still. It was arms day, so I won't flex too much, but just to slide it in there, just to get a little bit of the ego. Other than that, though, walked my way back, went on call with a friend, and relatively enjoyed that part of the day. Came back home, showered, just a little bit of backstory. Now, sat down, played a little bit of chess, and then I got straight into chemistry. And chemistry, I actually have a lot to talk about, because this is 4U chemistry, so grade 12 chemistry at the university level. And what I learned today in this past couple days, I would say probably, I want to say Friday was the last day where my teacher really introduced the new unit that we're doing instead of grade 11 review, which was also great because I had grade 11 chemistry last semester because I didn't take it the year, but I didn't take it in grade 11. That's why. But I took it last semester, did great in it, and now I have the grade 12 chemistry. Thank God. So now we're gonna recline the chair. Okay, perfect. We'll get a little scooch in here. So after we had done a little bit of review from grade 11, we finished our grade 11 review. It went over pretty good. I don't know if I like this. It's not bad. No, I rather have a sit up, keep it professional. Get the leg up on the other leg. Anyway, so we went over some scientists. I got my notes and the textbook in front of me to the left here, so I'll just refer to it slightly. But she introduced the development of the atom theory, and we went through a whole bunch of scientists who had contributed to it. She highlighted which ones are most important, and I'll just briefly go over them. So J.J. Thomson and his introduction with the raisin bud model. So essentially what that was he thought that there were just so the raisin bud model was that there's just general protons, which makes up the majority of the bun, and then each raisin is like an electron. And if I just let me look over that. Yeah, so electrons embedded in a positively charged sphere. Nice. Got that one before I look at the notes. Then Robert Millikan. So Robert Millikan, I don't know why I wanted to call him Mr. Millikan, as if I can't do him like that. But Robert Millikan, we covered in physics as well, which I took last semester. And we went on with the Millikan experiment, where he put oil droplets into a whole like mechanical concoction, which I understand roughly. Mainly what I get out of it was he was measuring the charge and mass of an electron, which, if I remember, was 1.602 times 10 to the negative 31. Negative 19. Oh, I got that so off. Coulombs. Yeah. And yeah. Okay, so I used two charged plates, and the drops became charged. Yeah. Okay. Damn, that was one hell of a like a experiment. And then Ernest Rutherford, and he proposed that the atom had a nucleus, kind of counteracting J.J. Thomson's original just electrons embedded in a positively charged sphere. And so after that, yeah, he kind of founded the nucleus, and he said that electrons were rotating around it. So he did the gold foil experiment. Gold foil experiment, yeah. And I believe he sent alpha particles. Is that what they were? Alpha radiation. I'm gonna say alpha particles because I like it. Sounds better. And he shot it at this gold foil. What he expected was the electrons to go straight through it, but they didn't. They actually some went through it and some bounced back at different angles in different directions. And so that's where he proposed that because it's not just one charge, there's it's not just it's not just protons and electrons. There must be something else, like a dense combination of the two. Let's call it that. And so that's where you get those particles bouncing back, because not all of them are going to pass straight through. Then continuing on. Oh, these are okay. I like these ones. So Niels Bohr contributed a lot. He contributed the emission spectrum and the absorption spectrum. So essentially, he did a lot more than that. I'm not gonna talk about all of it, but basically, he says that there are discrete energy levels in which electrons exist at, and they can only be at one or the other, never in between. And so, given a certain given energy or taken energy from it, you can jump between these electron levels. And you have Albert Einstein with regard to the electron. He contributed a lot more, and I'll definitely talk about. Actually, I'll go off on a little tangent. So in my physics class, our last unit was special relativity, and we covered Newton's mechanics, which I found, at least on a moral level, really crazy. So my teacher, and this was after talking about Heisenberg, Rose, what's his first name? Where's the Heisenberg guy? Was it Werner? Werner Heisenberg. Sorry about that. So this was after covering that. Oops, sorry. So what he kind of told us was that because the brain is essentially just like lots of electrons just passing, thoughts are just signals of electrons that just are passing through. And so he stated in some way, I'm gonna summarize it as best as I can, because this is summarization is what I'm really good at. Specifics not so much. But he kind of stated that in Newton's mechanics, from the time that you're born to the time that you die, everything and anything that happens to you, or that you think or do, is already predetermined. And I like to think of it like, because it's really only about your thoughts and how electricity works, or like electron signals. I don't know how to say it, but something along those lines. Because that is already predetermined, it already determines the rest of your life, because your thoughts, they turn into actions. Sorry, is it like that? I don't know. I don't know how it works. Your thoughts become words. Words. No, no. Your thoughts become habits, and your habits determine who you are. Something like that. But I just thought it was a pretty cool tangent that physics could basically determine the rest of your life, which is awesome. So let's disregard all the other moral dilemmas that we have going on, and just boil it all down to physics made me do this. Big tangent. Lots of arguments that may show up sometime down the line. We're not going to worry about that right now. But then we have Max Planck. I love his last name, and I learned Planck's constant, 6.63 times 10 to the negative 34 for optics in physics. Great guy. And he started the quantum revolution. So a couple bullet points here. So he proposed. I don't want to cover more than him than quantum revolution, to be honest, because I have a lot more stuff that I have to define. And then Heinrich Hertz giving our wonderful E equals HF. So the photoelectric effect, which we also covered in physics as well, funny enough, they really intertwined in this creepy way. And every time I see kinetic energy, I think EK. So he accidentally discovered the photoelectric effect, and that is essentially electromagnetic radiation hat. The photoelectric effect. Photoelectric effect is basically, to what I know, when you shine like a light on a metal, not all the like part of the light just not only refracts off the metal, but it also stays within it depending on the index of refraction of the metal. So that's a description intertwining what I'm getting here and what I know from physics. And we have Albert Einstein, and he hypothesized that light consists of packets of energy, or quanta, which he called photons. Great stuff. Let's cover three more, I believe. We have Schrodinger, de Broglie, or de Brogue, as my teacher likes to call him, and Heisenberg. And de Broglie spoke upon the duality of an electron, how it behaves like a particle and a wave. And then he had, I think, what was it, like the fastest Nobel Prize, and it was just a rearrangement of an equation. That's what my physics teacher showed me. And then we have Heisenberg's uncertainty principle, which is that you cannot determine the exact position and speed of an electron at any point in time, the exact speed and the exact position. So either you get the exact speed, position and momentum, I believe, right? Oh no, they're saying velocity. Location, yeah, position or velocity, so position or speed. I think I've also heard momentum talk about it as well. I think that was in physics. Let's go with velocity for right now because we're talking about chemistry. And so I find that really like weird, to be honest. I understand that you can't determine it because whatever you're gonna use to determine that is also made of electrons and matter, and so it like at an exact like a very fine at a very fine like measure. Like if you're trying to be very very accurate, it just can't happen. according to Heisenberg. That may be proven later down the line. We won't delve into it too much right now. Let me know if I should make like individual episodes. I honestly made this just after studying it, and it's fairly late at night, and so I'm going to go off on a few tangents, and my explanations aren't going to be the best, but my whole purpose of this episode was to briefly go over everything to kind of consolidate my learning for today. And lastly, we have Erwin Schrödinger with wave mechanics and how you can find the approximate location of an electron in an orbital. Sorry. So, finishing off with orbitals, or sorry, moving on with orbitals, we have quantum numbers. Now, this is where I'm going to try and shine here with my absolutely candid knowledge that I learned today and the past couple days. So, quantum numbers, at the very least, we have 4 quantum numbers. We have the principal quantum number, we have the secondary quantum number, we have the magnetic number, and the spin number. So, we'll keep it in and out of field. I'm not too picky on that. So, the principal quantum number determines the energy level. So, as when n equals 1, you have 1 energy level. When n equals 2, you have then sublevels. So you have an S sublevel, and then you have, I think at 2, the secondary number. Okay, we're gonna not go too in depth. We're gonna keep it generic. Principal quantum number, energy levels, like how much energy is associated with that level. 2, the shape. 3, the magnetic pole, so from -1 to +1. And 4, spin up by half or spin down by half, because you can't have two sets of electrons with the same quantum numbers and the same sublevel, according to Pauli's exclusion principle. And so one gets to spin up, one gets to spin down. And then we have a whole lot of definition and terms that we can go to. Not sure if I really want to go through with this right now. Like, it's just like defining electrons. Electron is a negatively charged subatomic particle. A proton is a positively charged subatomic particle. We have the emission spectrum, which is it's the wavelength of all light at a specific spectrum. And then we have the absorption spectrum. Hold on, this is the electromagnetic radiation by atoms all return to a lower energy state from a higher energy state. Continuous spectrum contains all the wavelengths in a specific region. Yeah, so the continuous spectrum is like kind of like the rainbow. Line spectrum, wavelengths and characteristics of an element being studied. Yeah, so those ones I'll look over later. So let's see if we have any cool ones we can talk about. A wave function, the mathematical probability of finding an electron in a certain region of space. Yeah. I mean, if you guys want to go over like definitions and key terms, you can definitely do that. But for right now, knowing that I kind of just told myself everything that I kind of need to, I'm pretty satisfied for right now with what I got. We're also closing in about 30 minutes. And I don't know if YouTube will let me upload one longer than that. So I'm going to close our textbook. It's 10:02. Kind of getting closer to... I'm not going to go to sleep. So let's close the pencil case and let's get a little bit deeper, just on a personal level. Let's get some water because my throat does get parched. So I'm gonna pack my stuff up and then I will get back to the video in 1 second. Oh yeah, I forgot my clothes were in here. Totally forgot about that. Let's take these out. Move to the side. This is good pants. Those bad boys in there. I want to review chemistry tomorrow. Physics, calculus is fine right now. Let's put that bad boy in there. Chemistry, thumb in there. Calculator. That's that. Okay. So let's move this a little bit closer. Don't do that. There we go. Okay. So what do we want to talk about? 3.5 minutes. I don't know. I think honestly, like, I think I'm satisfied with what I've done for today. Yeah. You know, I'll finish off with something. I find that if you ever kind of like getting to a point where I don't know where to go with this. I want to finish off with a motivational banger, but I can't. I want to see something that's on my mind, but really, at like this point in time, I'm just ready to go into this new week. And I'm waiting on midterms, looking to see what universities want to take me. And hopefully, one of them kind of clicks on this video and gets a little bit more idea of what they're dealing with. So, thank you to anyone who's watched or gone through this far. Hopefully, you learned a thing or two. And I just want to say, finally, I remembered. If you're ever at a point where motivation's kind of tough to get, or you don't feel as inclined to keep working, just remember that even if you're not doing it, even if you're not doing what you're doing because you love it, some of the greatest people and some of the greatest things accomplished weren't done just because one person wanted to do it, just because it was his own ambition. It was, at least from where I stand, from what I'm doing and what I take with me every day, and what I think of when I'm at my lowest, is that I don't do it for me. I like it. I enjoy what I do. I enjoy the studying. I enjoy going through tough problems, solving them, and just slowly but surely, not only increasing my own worth, but I do it for the people that love me and the people that care for me. And I think that if everyone cared a little bit more about everyone else, then everyone would have a nicer life, or a bit easier life. So thank you for going on this video. I hope you enjoyed it. Have yourself a great day.